An abstract for this presentation. So it's not really oriented toward nuclear power. It's really about energy resources used to generate electricity. And hopefully by the end of this you'll understand the title of my presentation. So the purpose of the presentation is basically to put those energy resources that we use to generate electricity in a proper non-political perspective. And so I'm going to give it a very brief discussion of energy itself. Energy is not a physical quantity that can be measured directly, but rather it's a property of things that gives them the ability to perform work. All right, there we go. Okay, so most likely everybody's familiar with the conservation of energy, which says that energy cannot be created or destroyed, but only converted from one form to another. And no work of any kind can be performed without the expenditure of energy. Energy can be categorized in a variety of ways. This is one way that can be categorized, and these forms can be categorized. And this slide actually illustrates how different energy forms may be manifested. Now, those are probably too small for everybody to see the various illustrations, but some of them are interesting. Some of you kind of scratch your head and say, wait a minute, how does that work? But anyway, I found this on the internet. I found it to be rather informative. And if you want to know about kinetic versus potential energy, those are both shown at the top there as kind of subcategories of mechanical energy. Okay, so not all energy is useful, and in doing work, some energy ends up getting dissipated as waste heat. So we can talk about available energy, which is that portion of energy that can theoretically be converted into work. Useful energy, which is that portion of energy that actually is converted into work. And the ratio of the two, ratio of useful energy to available energy, is called the energy conversion efficiency. Now, the only energy conversion process that's 100% efficient is the conversion of any energy form directly into heat, which is the end state of all energy forms in the universe. Okay, so this slide gives you a very, very brief history of energy. It provides or highlights the types of energy resources, their energy densities, and some general associated benefits and shortcomings of each of three historical energy eras. Pre-industrial revolution, the industrial revolution, and of course the post-industrial revolution. And the key here is the energy density, which is highlighted. All three of these are given in kilowatt hours per kilogram. And the energy density of available resources is key to understanding the evolution of human civilization. With the development of technology came access to energy resources of greater energy density. And energy resources of greater energy density provided humans with more abundant energy, allowing progress beyond the survival mode of living. Energy density of resources is also key to understanding, key to minimizing environmental impact while also meeting an ever-increasing demand for energy. And it is noteworthy that public fear of nuclear energy has restrained the progress in achieving abundant, affordable, and reliable energy for humanity that minimizes adverse effects on the environment in the post-industrial revolution era. So we're going to, as I said, look at primarily energy resources used to generate electricity. And there are three important considerations in choosing energy resources to generate electricity. One being, of course, the energy density, which determines the actual amount of the resources necessary to produce a desired amount of electricity. Energy conversion efficiency is a performance measure for any system converting an energy resource to electricity. And capacity factor is a performance measure characterizing the ability of electricity generating systems to provide a nameplate rating output. So system energy conversion efficiency and capacity factor performance measures will be further addressed a bit later in this presentation. But we're going to first consider how energy resources are used to generate electricity. So we'll begin with fossil fuels. The type of energy, of course, is chemical. Reaction of fossil fuels or hydrocarbons with oxygen converts chemical energy into thermal energy. Fossil fuels powered the Industrial Revolution and continue to provide the majority of our electricity needs today. They made possible the machines that make life easier for our predecessors, and they power the technology that dominates our lives today. Fossil fuels are used as a heat source for a steam cycle power plant to produce electricity, and they account for the majority of electricity generation in the U.S. So what we're talking about here in terms of a chemical reaction is shown here. We can use the burning of methane as representative of the burning of any hydrocarbon fuel, and the energy released in this reaction is about 50 kilojoules per gram of methane, or about 14 kilowatt hours per kilogram. And as I said, the energy released from burning most hydrocarbon fuels can be used to produce steam that becomes the working fluid in the steam cycle power plant. And here's what I mean by a basic steam cycle power plant. Here what happens is you use a boiler to create high pressure, high temperature steam, which is used to drive a steam turbine that also then can drive either industrial machinery or an electrical generator to produce electricity. And the low temperature, low pressure steam from the turbine exhaust is condensed back to water in a condenser, which is then pumped back into the boiler to start the cycle all over again. The next one is nuclear energy. Of course, the resource is uranium. The type of energy is nuclear, means it comes from the nucleus of the atom. And uranium fission converts nuclear energy to thermal energy in nuclear reactor fuel elements. Nuclear energy has been used almost exclusively as a heat source for a steam cycle power plant to produce electricity. And nuclear energy accounts for about 19% of the electricity in the U.S. Electrical grid. Here's what actually goes on in the uranium. An atom of uranium-235 captures a neutron, becomes unstable, fissions to produce two lighter elements, and gives off 2 to 3 free neutrons in the process. The splitting of the uranium-235 atom releases about 200 million electron volts of energy, or about 22 million kilowatt hours per kilogram of uranium-235. So the uranium-235 fission produces about 1.5 million times more energy than the combustion of hydrocarbon fuels. Next one we're going to look at is solar energy. The type of energy is radiant energy in the form of photons. The radiant energy or photons incident on a photovoltaic panel is converted directly to electricity or to thermal energy, waste heat, depending upon the photon energy. The U.S. government became heavily involved with solar energy research and development in the 1970s and began creating grants and tax incentives in the 1990s to make rooftop solar electricity generating systems viable and affordable for American homeowners. And as of 2020, solar energy provides about 2.3% of U.S. electricity generation. This next slide is to show how the photons are converted either into electricity, DC electricity, or into waste heat, depending upon the photon energy. So photons with the right amount of energy excite electrons that flow through wires to power our homes. Photons that are too strong also excite electrons, but their extra energy causes the cell to heat up, and photons that are too weak can't excite electrons and just add to the waste heat in the solar cell. Since they exhibit different wavelengths, photons exhibit different wavelengths, and since no material absorbs electromagnetic energy of all wavelengths, some photons then, of course, produce useless waste heat in the solar cell. And this graphic here shows how that's done. The photon is absorbed by material that has an excess of electrons, which knocks the electrons out of the material. They flow through a wire and end up coming back into a material on the other side of the material that is deficient in electrons. And that's how the electrical circuit is set up in a solar cell. Free electrons are produced in one of the materials by absorption of the incident photon energy. They flow through the electrical conductor to the other material, which is deficient in electrons. Okay, wind energy, the next one, type of energy is kinetic energy, or the air mass in motion. The wind turbine converts kinetic energy to mechanical energy in a rotating shaft, which then drives a gearbox and an electrical generator to produce electricity. From 1974 through the mid-1980s, the United States government worked with industry to advance the technology and enable large commercial wind turbines. As of 2020, wind energy produces about 8.4% of the U.S. electricity generation. Here's what that system, or what a wind turbine looks like. You've got your rotor hub driving a low-speed shaft, which then goes through a gearbox to drive a high-speed shaft, which then drives the electrical generator to produce the electricity. The next one is water energy. Type of energy, again, is kinetic. This is water mass in motion. And a water turbine converts the kinetic energy of water into mechanical energy in a rotating shaft, which then drives an electrical generator to produce the electricity. Today, the United States has over 2,000 hydroelectric power stations that supply about 7.3% of the country's total electrical production output. And here's a graphic to show what we're actually looking at when we're talking about hydroelectric facility. We've got a reservoir of water behind the dam. Water is directed to the water turbine through a penstock, and the water turbine then drives the electrical generator, producing the electricity. The energy density of the flowing water depends on the difference in elevation that imparts a specific velocity or speed to the water. Okay, so there is no such thing as clean energy. There's both positive and negative aspects to obtaining useful work from all energy resources. There are both direct and indirect costs associated with acquiring resources and manufacturing the equipment and facilities that are necessary to produce useful energy we consume in our daily lives. So the entire life cycle associated with using any energy resource to obtain useful energy results in byproducts and waste that can adversely affect the environment. What do I mean by energy resource life cycle? Well, that's what this particular slide shows. There are various, or a number of phases to the life cycle, beginning with the raw material extraction, then manufacturing, production, transportation, final utilization or reuse of the end product, and then waste disposal. So to get the complete picture of the cost of generating electricity from an energy resource, one needs to look at the entire life cycle for the energy resource. And physical materials are required for constructing and operating energy conversion facilities, for manufacturing machines and devices used to convert energy resources to electricity, and for manufacturing the devices and equipment used to convey that electricity to the electrical grid. So the first phase is the raw material extraction and refining. Raw materials must be mined and processed to obtain useful building and manufacturing materials. And the processed material resources are required for the construction and operation of facilities, both, well, to refine the raw materials initially, facilities that manufacture the machines, devices, and equipment for energy conversion, electricity transmission, and finally, facilities for converting the energy resources to electricity. The next phase is manufacturing and production. Structural materials for constructing the facilities to refine the raw materials, manufacture the energy conversion devices and equipment, and convert the energy resource to electricity must be produced. And the machines, devices, and equipment for operating these facilities must be manufactured. Transportation phase. Transportation resources are required to get the raw materials to the refining facilities, the processed materials to manufacturing facilities, the construction materials and equipment to facility construction sites, and the machines, devices, and equipment to the energy resource conversion locations. And the last phase of the process is the waste disposal or recycling. Waste are produced in every phase of the life cycle, as well as equipment and structures that are no longer usable, that require appropriate dispositioning. So we'll next consider the electricity generating system performance, which is an important feature when deciding among available electricity generating technologies. One of those performance measures, of course, is efficiency, and this is the ratio of useful energy to available energy. The other is the capacity factor, which is the ratio of actual electrical energy output over a given period of time to the maximum possible electrical energy output over that time period. And so these are both important parameters that characterize the performance of electricity generating systems and facilities. Now, we can find that or calculate that efficiency performance factor by using information such as shown in this slide here. This is a energy conversion table that shows on the left column, it shows the initial energy form, and in the top, it shows the energy converted, or the energy form that's converted from the initial energy form. So for example, if we wanted to find how mechanical energy is converted directly into thermal energy, we find the mechanical energy in the first column, and we go over to the thermal energy on the right, and it shows brake drum, and of course that's 100% efficient device because it converts the mechanical energy directly into heat. Okay? So we can use these kinds of, or this kind of information to determine what the efficiency of a system, electricity generating system is. So let's start with a coal-fired power plant. This diagram here shows the configuration, typical configuration for a coal-fired plant. And for the chemical to electrical energy conversion, the energy conversion devices are the boiler, the steam turbine, and the electrical generator. So going back to that table, we can find converting the chemical energy to thermal energy in a furnace of the steam boiler. It shows it's 85 to 88% efficient. We can then find the conversion of thermal energy to mechanical energy in the steam turbine over there on the left, which is only 40 to 47% efficient. And finally, the conversion of mechanical energy to electrical energy in the electrical generator, and that has an efficiency of between 95 and 99%. Now, we can use that information in a convenient form like this to find how we get the system efficiency. We start with the primary energy carrier, in this case being coal. The first conversion device is the boiler. We can put the 85% efficiency. We use the minimum efficiency of 85%, put that in there. The next energy conversion device is a steam turbine. Once again, using the minimum efficiency of 40%, put that in there. The final energy conversion device is the electrical generator, again using the minimum efficiency of 95%. We can multiply those all together and we find out that when we get to generating the electricity, the system efficiency is about 32%. And that's in this case, a minimum efficiency because we've used a minimum efficiency for each conversion device. Now, as I've pointed out to people, that system efficiency doesn't sound very good, 32%, because what it means is that essentially 2/3 of the energy we started with has been dissipated in the environment in the form of heat. But the laws of physics are what they are, and we can't change them. It turns out that the steam cycle is the most efficient process we have for generating electricity using fossil fuels as well as nuclear energy, and that's why we use it, because it's the most efficient. Okay, the next one we can look at is the boiling water reactor plant, being the simpler of the two types of nuclear reactors. This graphic illustrates the configuration of a typical BWR. The energy conversion devices are the nuclear reactor, the steam turbine, and the electrical generator. So now, in this case, again, we can use this nice graphic for filling in the information. Primary energy carrier being uranium. First energy conversion device is the nuclear reactor. And greater than 90% of fission energy is actually recoverable as heat in the nuclear fuel. Therefore, I've chosen the minimum efficiency of 90% for that energy conversion. And of course, the steam turbine and electrical generator are the same as we used in the last case for coal-fired power plant. So when we put those numbers in, we finally find that the electricity generating efficiency is about 34%. Okay, next one we're going to look at is a hydroelectric power plant. Again, here we have an illustration of what that would look like. The energy conversion devices are the hydraulic penstock, the water turbine, and the electrical generator. So again, going back to this particular table, we can find converting the kinetic energy of the flowing water into mechanical energy in a water turbine is about 86% efficient. So we can put that into the form again. In this case, the primary energy carrier is water. First conversion device, the penstock. So while there's a minimal energy loss in a penstock, a minimum efficiency of 95% is being used in this case. I was never able to find anywhere on the internet any mention of efficiency of hydroelectric penstocks. I'm assuming they're probably pretty close to 98, 99% efficient, but I just chose 95 as the minimum here for this particular calculation. Now, water turbine, I've used the 86% from that table. Turns out that for large modern water turbines, they can operate at mechanical efficiencies of greater than 90%. But again, I'm going to use the minimal number here for this calculation. And the electrical generator is the same as we've used for the fossil fuel plants and the nuclear plants, so that's 95% efficient. We multiply those numbers out, we find out that the efficiency of converting kinetic energy of water into electricity is about 77%. Next one we look at is the photovoltaic facility. This is a diagram of what such a facility would look like. The energy conversion devices are the photovoltaic panel and the DC to AC inverter. So now, I can't go back to that nice table I have because a lot of the information just isn't there. So in this case, we only have two energy conversion devices. The energy carrier, of course, being the photon. Now, the energy conversion efficiencies chart indicates an efficiency range of 15 to 27%, if you want to go back and look at that. For solar cells, solar cell efficiency is a measure of how much of the electromagnetic radiation incident on the cell is actually converted to electrical current. And photons above a certain energy level will create electrical current in the panel, while photons of less energy will deposit thermal energy in the panel that's ultimately lost to the environment. In fact, the physics boundary for silicon PV photovoltaic cells, called the Shockley-Kaiser limit, is a maximum conversion of 33% of photons into electrons. And most photovoltaic panels are between 15 and 20% efficient. High-quality panels can exceed 22% efficiency in some cases, but the majority of panels do not achieve efficiencies above 20%, and so that's what I've used for the value here for the radiant to electrical conversion, 20%. And although DC to AC electricity conversion is not included again in that energy conversion efficiencies chart, a typical solar inverter has an efficiency of greater than 94%. So I've assumed again the minimum efficiency of 94% here for that DC to AC inverter. So again, multiplying these all out, we find out that the conversion efficiency for a photovoltaic facility is about 19%. And the final one we're going to look at here is the wind turbine. Again, the wind turbine consists of a rotor, blades, the rotor blades, the gearbox, and the generator. Again, going back to this nice diagram, the primary energy carrier is wind. The first conversion device is the rotor blades. Second is the gearbox, and the third is the electrical generator. Now, with these, I had to go find this information. Turns out the Betz limit specifies that no wind turbine can capture more than about 59% of the kinetic energy of the wind. That's when the wind exit energy, the exit wind velocity is about 30 to 40% of the incident wind velocity, 59%. Typically, however, wind turbines have a maximum efficiency of around 40%. And that's when the wind exit velocity is about 70% of the incident wind velocity. So 40% is the number that's used there for the kinetic to mechanical conversion. Now the efficiency of gears with high gear ratios range from 75 to 95%. And if we use a typical gearbox efficiency of 85%, together with a maximum permanent magnet generator efficiency of 95%, then the system would have an efficiency of about 32%. In this case, though, I've used the maximum gearbox efficiency of 95%. Then the maximum system efficiency is about 36%. And by the way, a permanent magnet generator requires no exciter, slip rings, or brushes, and requires very little maintenance because it can be completely sealed, which is why we primarily use permanent magnets for wind turbine generators. Okay, so we can summarize all that with this slide showing the electricity generating system efficiencies. The highest being the hydroelectric plant at 77%, the lowest being the photovoltaic facility at 19%. Okay, next let's go to the capacity factor. So electricity generating system capacity factor is the ratio of actual electrical energy output over a given period of time to the maximum possible electrical energy output over that time period. And this slide shows the conditions that actually affect the capacity factors of those kinds of facilities. In other words, they're dependent upon equipment failures in the facility, routine maintenance, electricity demand, for example, for load following units, and this is primarily directed at hydroelectric facilities, which in a lot of cases are used as load following units. Fuel availability, for example, sun and wind, because the sun isn't out 24 hours a day and the wind doesn't blow at the right speed all the time, if at all. And then there are environmental regulations that also affect the capacity factor. In other words, a lot of coal-fired units today are not allowed to operate at their 100% capacity factors by regulatory agencies. So if we look at system capacity factors, we find out that the largest average capacity factor is with nuclear. It's 92%. Hydroelectric is about 41%. Coal 40%. Wind turbines about 35%. And photovoltaic facilities about 25%. And if you look at this, of course, you can convert that into equivalent full power days per year. So based on the capacity factor, nuclear provides essentially 336 equivalent full power days per year. Hydroelectric about 150, coal about 146, wind turbines about 128, and photovoltaic facilities provide only about 91 equivalent full power days per year. Note that these are the average capacity factors. So capacity factors will naturally vary from facility to facility. Facility maintenance outages is the primary influence on capacity factor for nuclear, geothermal, coal, and natural gas facilities. Energy resource availability is the primary influence on capacity factor for photovoltaic and wind turbine facilities. And load following operation and water availability are the primary influences on capacity factor for hydroelectric facilities. And what a capacity factor of 25% for photovoltaic facilities means is that to obtain a year-round average of 100 megawatts actually requires a facility with a nameplate rating of 400 megawatts. Okay? So if you're required to produce 100 megawatts of electricity, you need 400 megawatts of installed capacity because the capacity factor is only 25%. Similarly, a nuclear power plant with a nameplate rating of 1,100 megawatts delivers a year-round average of more than 1,000 megawatts. Okay, so now let's talk about the problem with 100% renewables. Not all energy resources are equal. There are two types of demand on the electrical grid that must be accommodated. One is called baseload electricity, the other is called peak load. Baseload electricity is that minimum level of electricity demand required over a period of 24 hours. Peak load electricity is that maximum level of electricity demand that exceeds the baseload level required over a sustained period of time. So, let's take a look at a typical U.S. daily electricity demand. And you can see, in this case, the top, not working again, worked earlier. Okay, the top one is the summer daily electricity demand. There we go. Top one is the summer, this one is the winter, and these two are the spring and fall. Okay? So you can see how the daily demand for electricity varies as a function of the time of day. Okay? And the energy demand on the grid varies not only by the time of day, but also the day of the week, the temperature, the latitude, the location, and the seasons, as well as a number of other factors. The morning ramp-up begins at about 6 a.m., and the demand returns to baseload level at about midnight. The extended summer peak electrical demand at about 20,500 gigawatts, as shown in this particular graphic, occurs from about noon to 7 p.m. And the extended winter peak demand at about 18,500 gigawatts is more pronounced and occurs from 6 to 7 p.m. This is another graphic to show a little bit more information about how that total demand profile is generated. This is a typical California daily demand load profile, and this displays the variation of California's electrical demand on a hot day in 1999, it turns out, and shows the specific user sector demands that contributed to the total electrical demand. The morning ramp-up began about 8 a.m. and returned to baseload demand at about midnight, and the extended peak electrical demand on the California grid at about 50,000 megawatts in this case occurred from 2 p.m. to 6 p.m. So with that in mind, let's look at the photovoltaic panel efficiency versus the time of day. And this graphic shows that efficiency in two cases. One is a static or fixed photovoltaic system. The other is a sun tracking system. So a static PV system is not well suited to providing peak load electricity for most U.S. locations, since the daily time interval of panel peak output is from noon to 3 p.m., which does not match well with the daily time interval of peak summer demand, which is from noon to 7 p.m., or for that matter, the winter demand, which is from 6 to 7 p.m. Sun tracking PV system with a daily peak output interval of 9 a.m. to 5 p.m. is a much better match for the summer daily peak demand. And although a sun tracking PV system may be well matched for the high air conditioning demand in the middle of a summer day, when the sun goes down and the temperature doesn't, another source of energy must be available to provide that energy load. Okay, and with regard to wind turbines, this graphic shows how wind turbines don't produce rated power until a sustained wind speed of 12 meters per second, or about 26 miles per hour, is achieved. And such sustained wind speeds are really uncommon in most areas of the United States. So not only is wind energy not suitable for baseload electrical demand, but its undependable speed in most U.S. locations also makes it unsuitable for matching peak electricity demand as well. Okay, let's look at some other realities here with regard to renewables. We can only derive reusable energy from renewable resources by using materials that are not renewable. In fact, old solar and wind equipment generates millions of tons of waste. Much of it is toxic. Electric car batteries require mining, moving, and processing more than 500,000 pounds of raw materials from somewhere on the planet. And following a 7-year life, electric car batteries have to be disposed of with major toxic waste implications. Most life cycle waste from using renewable energy resources to generate electricity cannot be recycled. So eliminating fossil fuels and nuclear power would require a massive worldwide increase in mining for lithium, cobalt, copper, iron, aluminum, and numerous other raw materials. And producing wind turbines and solar arrays and energy storage batteries requires mining, moving, and refining vast amounts of earth. So when the entire life cycle for generating electricity from renewable energy resources is considered, renewable resources are really no more environmentally friendly than fossil and nuclear resources. So building wind turbines and solar panels, as well as batteries, backup batteries, requires on average more than 10 times the quantity of materials compared with building the machines for hydrocarbons to deliver the same amount of energy. Hydrocarbons are also needed to produce the concrete, steel, plastics, and purified minerals that are used to build the green machines. So you can't use, basically we're saying here, you can't use renewable energy to produce these other materials that we need, because you need hydrocarbon fuels for that. So the use of hydrocarbon resources cannot be totally eliminated by renewable resources. Let's take a look here at the minerals used in the energy technologies. This graphic compares the quantity of materials required for alternative transportation and power generation technologies. So the top, it's called transport. We have the electric car and the conventional internal combustion engine driven car. And you can see the difference in the amount of minerals that are needed for both of those technologies. And note the scales. So in this case, the upper scale there, we're looking at 50, 100, 150, etc. Kilograms per vehicle. These numbers right here. And down here for the power generating facilities, we're looking at kilograms per megawatt as the unit. Okay, so it's clear that renewable energy generated electricity is going to require a lot more metals and other minerals than fossil fuel and nuclear generated electricity. And electric vehicles are going to require a lot more of these metals and minerals than internal combustion engine powered vehicles. And most equipment needed to mine and transport green energy material must run on diesel fuel because they're too big and heavy to be powered efficiently by batteries. Also missing from the discussion is the $500 billion or more cost associated with 500,000 miles or more of new transmission lines that are required to connect the 50,000 plus wind and solar facilities for an all renewables electrical grid. And then there's the battery problem. 100% renewables require backup battery energy storage systems, and this isn't anything but a trivial matter. Backup energy storage requirements are absolutely staggering. The issues not being addressed include how many batteries would be required to provide adequate backup electricity to the green grid when parts of the U.S. experience extended wind and sun downtimes. Do sufficient raw materials even exist? And how would we dispose of the huge amounts of toxic waste from battery manufacturing? Charging backup batteries requires off-grid wind and solar energy. That is, energy that's not needed to satisfy the immediate electricity demands of the grid. So the off-grid system must be designed to provide a charge current capable of recharging batteries quickly and efficiently, and within the window of time that the on-grid system is actually generating peak power. And lithium-ion battery energy storage systems are generally designed for only a few hours of energy storage, which may be enough to accommodate daily swings in solar and wind electricity generation, but absolutely insufficient to accommodate long periods when the sun and wind are unavailable. The efficiency of storing and recovering wind and solar energy is 60 to 70% for lead acid storage batteries and 87 to 94% for lithium-ion batteries, which also then adds to off-grid wind and solar facility requirements. Because they aren't 100% efficient, you need more of them to generate the amount of electricity needed to charge your backup battery system. Also, lithium batteries contain both the oxidizers and fuel within the enclosed battery space, and therefore carry a risk of fire and explosion in the case of overcharging, over-discharging, or excessive current, or short circuits. Currently, there is no single standard for assessing battery safety, and there is no fire prevention system design standards or test criteria for battery energy storage systems. So here's an example. Backup battery energy storage system must be more than a short-term concern. In this case, the New York State Climate Leadership and Community Protection Act, which was passed in New York, requires 3,000 megawatts of battery storage to be built by 2030 at a cost of around $9 billion. I'm sure that cost is going to go up, which will provide about 10,000 megawatt hours of electricity over 4 hours. And in 2019, an average daily electricity consumption in the state was around 384,000 megawatt hours. So on a typical New York winter day when the sun doesn't shine and the wind doesn't blow, all of that battery storage would provide a little more than a half hour's worth of average daily use at current electricity consumption levels. So I'm not sure what the state of New York is up to here, but they don't seem to have their heads on straight. So this is where your smart home energy utilization system with remote control by the local utility authority starts to become a reality. So let's look at currently affordable battery energy storage system. The Tesla Megapack, which is a container-sized 3 megawatt hour battery energy storage system costs more than $1.2 million or more than $400 per kilowatt hour. Now, due to the economy of scale, an installation of 100 of these megawatts brings the cost down to around $280 per kilowatt hour. But for comparison purposes, the U.S. average cost of electricity for the month of May 2021 was 13.71 cents per kilowatt hour for residential customers and 10.65 cents per kilowatt hour for all sectors of the economy. In addition, there is an additional annual maintenance cost for Tesla Megapacks that's estimated to escalate at about 2% per year. So the scale necessary to supplement on-demand renewable generated electricity, the cost of backup battery storage systems makes anything even close to 100% renewables economically impossible. All right, let's take a look at the supply chain problems for 100% renewables. This graphic shows the top 3 world producers of materials required for renewable energy facilities. And by the way, DRC stands for the Democratic Republic of the Congo. The U.S. renewable energy industry is very much dependent on foreign countries for acquiring raw materials. In 1954, the United States was 100% dependent on imports for 8 minerals listed in the Strategic Minerals Act of 1939. Today, the United States is 100% reliable for 17 strategic minerals and depends on imports for over 50% of 28 widely used minerals. And China is a significant source for half of those 28 minerals. Right now, the Congo mines 86% of the world's cobalt. Chinese companies own or invest in at least a dozen Congolese mines, and nearly 7% of the cobalt ore leaving the Congo is actually refined in China. In Australia, the top miner of lithium exports most of its lithium to China, which accounts for more than 60% of the world's lithium refining capacity. And here's another graph showing the world processing of minerals. Here as well, the U.S. renewable energy industry is very much dependent upon foreign countries for raw material processing. And you can see China is the world's leader in processing all of these materials. And in fact, China controls 90% of the battery industry's cobalt supply chain. So 5 of the world's top 10 wind turbine manufacturers are Chinese-owned or operated. 9 of the world's 10 top solar panel manufacturers are Chinese-owned or operated. And China is also responsible for 37% of passenger electric vehicles and 99% of electric buses sold globally since 2011. So the bottom line for 100% renewable energy is if all of America's electricity is to be generated only by renewable energy resources, America will always be dependent on foreign governments for the materials, and electricity will necessarily be rationed. And if all cars are to be electric vehicles only, there will not be enough electricity to keep them all charged. So a lot of us are going to have electric vehicles permanently stored in our garages because we won't be able to charge them. That's pretty much it for what I wanted to present today. If there are any questions, I'd be happy to try and answer them. Larry?
You didn't mention that anything or have a chart on the total life cycle cost of each one of those options from birth to death.
Yeah. That information,
by a whole lot, or?
That information may or may not be available. I'm sure it's not easy to come by. I didn't spend a lot of time searching for it.
Coal-fired plants and nuclear plants are pretty well known.
Yeah.
But the other ones are probably not so
right.
well known yet.
And there are reasons for that. Most of them not good. Yeah.
If I remember correctly, 40 or 50 years ago, the materials put in panels for satellites to keep them electrified was gallium arsenide. Is that still used today? It's pretty nasty stuff to manufacture and dispose
Yeah,
of.
it's pretty nasty stuff, as we know at Sandia. I don't believe any of that's being used for commercial photovoltaic facilities, but I don't know that to be 100% true. I think most of the photovoltaic panels today are silicon carbide or the cadmium tellurium for the, I think those are the two primary ones that are being used. Anybody else have any information about any other kinds of panels being used for commercial purposes?
Oh, Jeff, on Channel 7 in the evening, the meteorologist, Joe Diaz, gives a maximum renewable mix of your energy for that, the maximum. Day before yesterday was 41%. Yesterday it was 21%, I think. So it varies a lot. But what he's looking at is that PNM is publishing every 15 minutes the percentage of renewable energy that they're mixing into the grid. At the end though, you have what the average is for the day. So yesterday was at 21 or 23%, I think it was 21. The average for the day was 8%. And he mentions that at the end, but you gotta listen very closely to get that average. So when you see, I don't know if any of you watch Channel 7 News meeting, but when he gives that, kind of keep in mind that you're looking at two numbers. One is the maximum. That maximum might only be for 15 minutes. And he also gives a average. So watch the average.
Yeah, that's your capacity factor in action.
Yeah.
Yeah.
Also yesterday, there was or day before yesterday, an interesting article in the journal. And it has to do with the Ford F-150 Lightning, the new pickup truck. And that truck uses, the base model uses 1,000, let's see, that's 1,000 kilowatts. Let's see, no, 1,000 watts per hour. Well, anyway, the batteries in that model, the article used Texas as an example. And if you were to take all the vehicles in Texas, there are 22 million of them, and make them electric based upon what the F-150 will be getting. It'll take, if you plug them all in at once, you got 2,200 gigawatts of electrical power it would take to do that. That electricity doesn't exist now. That's an additional to the current base load that's out there. So I don't think any of us will live long enough to where we get to the point where there's some break even on renewable.
Yeah.
Jeff, I noticed you didn't really compare uranium and its availability to the other raw materials you were talking about that are produced and refined by foreign governments.
Oh, yeah, that wasn't in these charts, the uranium. Yeah.
And of course, uranium is the base load mineral that powers nuclear power. And it's not a rare earth element, but it is, I mean, like any generation, copper and a number of things go into it. Why didn't you include that?
That wasn't included in these graphs that I found. Yeah, we, to my knowledge, there isn't a shortage of uranium for the United States that we need to go overseas for. Although a certain person, not to be named, did sell our portion of Canadian uranium to the Russians a
Yeah.
few years ago, which I could never understand. Made no sense to me. I don't know what we got for it. I don't think we got anything for it.
We bought a lot of it from Russia before, so
Yeah,
that was during the megatons and megawatts where we didn't have to mine for almost 20 years because we were converting down-blended material out of nuclear weapon systems.
right. And here again, you know, when it comes to uranium or plutonium, in this case, we've got plentiful supplies of uranium and plutonium just waiting to be used. But politics, regulations don't allow us to use good nuclear fuel at this point. So what are we doing with it? Well, we're calling it waste. We're going to bury a lot of plutonium down at WIPP, and the unused uranium and the plutonium created in nuclear reactors, commercial nuclear reactors, still sits in storage at the various power plant sites. We're not going to be dependent on foreign sources for uranium or plutonium in the future unless we continue to say, well, we're so worried about this nuclear proliferation problem that nobody else in the world worries about, that we refuse to use the uranium and plutonium resources we have in this country.
And that's a little bit of what was said last week at COP26. If you've been following the news there, that was the big conference in Glasgow, is that, you know, nuclear really is a way to help alleviate and get us out of the global issue with climate change, but the people there didn't want to consider it, even though it was pointed out to them that 70% of the electricity that Glasgow was using to run the conference was nuclear. I'm not kidding. So
You can't make this stuff up.
you can't, no. Well, Jeff, thank you. This has been great.
Oh, I think we have.
So how can the Ford Motor Company justify coming out with an all-electric Ford 150 pickup truck?
Yeah, I saw, I don't remember which company it was, said by 2035, they're going to manufacture nothing but EVs.
Yeah.
And I'm thinking, really? I told my son-in-law, you want to know, earlier this summer, you want to know about electric vehicles. I said, don't buy one. I said, if you do, eventually it will be parked in your garage permanently because there won't be enough electricity to charge.
The electricity will be so expensive, it won't be advantageous economically like it might be now. I mean, did you see that Hertz said they're going to buy, what was it? 50,000. 5,000. 5,000 Teslas. And it's a fifth of the fleet. That's a lot. But where are they going to charge all that? There's not a station every corner yet.
Where do you plug it in?
Where do you plug it in?
Yeah.
Yeah.
So, you know, there are lots of things that aren't being discussed that have to be discussed. Lots of decisions being made, bad decisions. And I keep thinking, all right, so when is reality finally going to set in? I hope I'm not around when it does.
When we do away with fossil fuels, how are you going to get across the Atlantic Ocean?
A rowboat.
Well, it'd be nuclear power.
Yeah, we have to be nuclear.
It'll have to be the Savannah.
Well, you'll never have an airplane. It'll fly.
Electric powered Hyperloop,
Bring back the Savannah.
all the way.
What?
A Hyperloop.
Yeah,
Yeah.
All right.
Thank you,
We're gonna
Jeff.
come up there.
anyway.
All right.
Thank you, Jeff. Thank you all for being here. Again, if you have any ideas for a brown bag that you would like to present, please feel free to see me and we can get to work planning. And if you want to know more information, you can always go check out the Energy Encounter exhibit, which does have all of the different energy sources available, nuclear, hydroelectric, renewables, and solar. And you can check out the pros and cons there as well.